Hello mathematics, physics, and engineering students, and welcome to this series on the Laplace Transform. Before we begin, I want to give some quick background on myself so you can see the passion behind creating this content for you all. I'm a firm believer in setting a dream and being determined to reach that dream, and that's what got me through college. I was able to become a tenure-track professor by the age of 26 and then becoming tenured by the age of 30. A lot of students will ask me, what is it that was driving you when I was a student? And they're actually surprised to find out that my dream when I was in college was just to buy a Corvette. And I was able to obtain a career by the age of 26 to be able to buy my dream car. And it was one of the greatest feelings ever to put in so much work to go through getting a bachelor's, to go through getting a master's, and to go through all those nights of studying for years, and then to be able to do what you want. I was able to drive this car up the showroom floor, and it felt great. So my passion is to help all of my students and any other students out there to reach whatever goals they want to, whether you're trying to be a professor, whether you're trying to go into the industry, whether you're trying to be an engineer. I want to create some content to help you along the way in all your courses. So let's go ahead and get started now. I want to start off by giving an outline so you can see what the structure of this lesson will be about. I'm going to be starting off with the actual definition of the Laplace transform being the improper integral. And I'm going to compute an example of the exponential function using the definition. Then I'm going to follow up using the Laplace transform table to compute Laplace transforms of specific functions. So some more exponentials, some trig functions, and I'm going to show the linearity property of the Laplace transform and also apply it to hyperbolic functions. So the Laplace transform is defined as an integral transform of a function. What does that mean? We're essentially going to be plugging in the function into an integral, integrating that integral, and then it's going to return another function. The formal definition is given as follows. The Laplace transform of a function f of t is defined by, so we're going to use this curly L, and I'm going to do the Laplace transform of f of t. And as I said, I'm going to take this function and I'm going to plug it into an integral. And I'm going to integrate it against e to the negative st. Notice this is going to be an improper integral with limits from 0 to infinity. So the Laplace transform will exist only when this integral converges. Now, how do we use the Laplace transform in differential equations? Well, we're going to take a differential equation and we're going to apply the Laplace transform to that differential equation. What's going to happen is we're going to get a resulting algebraic equation, and then we'll solve that algebraic equation. After that, we'll invert it using the Laplace inverse, and it's going to return the solution of the differential equation. Let's begin our first example by taking the Laplace transform of an exponential function using the definition. So I'm going to compute the Laplace transform of f of t equals e to the at for some real number a. Now this looks like a simple function, e to the at, but it turns out this integral is going to get actually complex. It's really fun, I enjoy it, but we'll see how this works out. So what we're going to do is, going by definition here, the Laplace transform of f of t means that we take that function f of t, we'll integrate it against e to the negative st, and that'll be an improper integral, with the limits being from 0 to infinity. So let's go ahead and do that. The function that we're working with here is e to the at. So I'm going to do the Laplace transform of e to the at. I'm going to plug that into the integral, so I'm integrating e to the at against e to the negative st, again with the limits being from 0 to infinity. Well, using properties of exponents, I can combine the two exponents from those exponentials. And I'm going to write it in a very specific way, so I'm going to write it as e to the negative s minus a t. So the reason I do that is the relationship between s and a will determine if this integral converges or not. So we have to look at different cases. One when s equals a, one when s is greater than a, and one when s is less than a. So the first case we're going to look at is one of the easiest ones here. It's s equals a. So what's going to happen is we're going to look at the relationship here between s and a, and we're specifically going to plug in a for s. So that's going to take my integral and give me right here e to the negative a minus a. And the purpose of this one, why I say it's the easiest one, well, it just gives me e to the 0. And so that means I'm just going to be integrating 1. And if I integrate 1, I get an answer of t. And those limits will be from 0 to infinity. So when I plug infinity into t, well, this is just going to diverge. It's going to go to infinity. That means the Laplace transform is not going to exist when s equals a. And we will say the integral diverges. So here's where it starts to get a little tricky. That's going to be in case 2. And case 2 is going to be when s is greater than a. Let's consider our integral again. And before I do this, I want to do a little side note to show how to quickly integrate exponential functions. So from our calculus days, yes, we know how to do u sub, but there's a little shortcut for exponentials. All we do is we take the number and the exponent, this 5 here, and you're just going to multiply by the reciprocal. So I'm going to take the 5, multiply by 1/5, and the exponential is going to stay the same. E to the 5x was the integrand, and now it's just in the answer, e to the 5x, and I go plus c. So that's going to help us get this improper integral done really fast. And I go ahead and compute it here. What is it that I did? Well, the constant here was negative s minus a. This is similar to the 5 in the previous example. And I just multiplied by the reciprocal. So 1 over negative s minus a, and that allowed me to compute it pretty quickly. So let me go ahead and remove this side note and let's get back just to the problem we're working with. And now I want to go ahead and plug in the limits to see if this integral actually converges. So going from the previous step to this step, I took infinity and I plugged it in for t. And then I took 0 and again I plugged it in for t. I'm going to just clean this up a little bit. E to the 0 would just be 1. So we're looking at this answer of negative 1 over s minus a, e to the negative s minus a, essentially taking a limit as it goes to infinity, minus 1. So the problem here is that exponential, e to the negative s minus a times infinity. Does that actually converge? This is going to be dependent now on the relationship with s and a. S here is greater than a. So that means that s minus a is positive. Well, if that's positive, and this is negative, when I actually multiply those two out, this whole term is going to be negative. So I have a negative exponential, and negative exponentials will go to 0. So that term essentially is going to vanish. And I'm just going to be left with negative 1 over s minus a times it by negative 1. So that's going to clean up very nicely to just go into 1 over s minus a. And guess what? When s is greater than a in this case, the integral exists. The Laplace transform of the exponential exists when s is greater than a. Let's look at the last case here. Case 3 is going to be when s is less than a, and we're still looking at this improper integral. It's going to work out very similarly. It's going to give the same exact answer. The only thing now is we're still looking at, does that exponential converge? The difference here now is s is going to be less than a. So this term right here, if s is less than a, then s minus a would be negative. And therefore, if I multiply by another negative, this whole term in the exponent would be positive. So I have e to positive infinity, okay, or a positive exponential there, and that's going to take off to infinity. So this whole integral is going to diverge when s is less than a. So out of all the cases, the Laplace transform only exists in case 2 when s was greater than a. So we're going to go ahead and formally define it now. The Laplace transform of e to the at is going to equal 1 over s minus a, and that only is going to exist when s is greater than a. So here's the thing that I want to note, and it's common notation, it's in a lot of textbooks. We took the Laplace transform of e to the at. That was a function of t, and the answer that we got was 1 over s minus a. We can now view that as a function of s. So we take the Laplace transform of a function of t, and it returns a function of s. Because of that, most textbooks will start to use this notation. It's interchangeable. So you have the Laplace transform of f of t, and that's going to equal capital F of s to indicate that we returned a function of s. Let's go ahead and try some practice with some quick examples here now that we actually derived the Laplace transform for an exponential. So I'm going to go ahead and put that formula for reference over here. We're going to be taking the Laplace transform of e to the 3t and e to the negative t. And the way that it's done is you just want to figure out what the a value is over here in the formula and then plug it in. So when I look at the Laplace transform of e to the 3t, well, my a value is going to be 3. So when I actually solve this, it's just 1 over s minus a, or just 1 over s minus 3. And in part b, the a value here would be negative 1. So if I go negative, negative, or s minus minus 1, it turns to s plus 1. So for taking the Laplace transform of exponentials, you just plug in the number for the a, watch out if it's negative, it'll switch that denominator to being a positive, but that's how quick it's done once we actually have the formula derived. Let's now do the Laplace transform of some trig functions. Now we could take the sine and cosine function and we could plug it into the improper integral and actually integrate it out very similarly to how we did the exponential. However, that derivation is quite long, and to save some time in this video, I'm going to go ahead and just give the derived formula so we can reference and actually compute examples with. But you can find the derivation in most differential equations textbooks. It's actually a fun one to look over, so I recommend referencing your textbook to check it out. Well, let's just go ahead and start to work with these two formulas. The first one that I'm going to start off with here is taking the Laplace transform of a sine function. So part A of this example, I'm going to take the Laplace transform of sine of 2t. And it's just going to be referencing the formula. For this particular example, I'm going to look at the first formula here that we have. So I'm going to be doing the Laplace transform of sine of 2t. And just as we did with the exponential, I just want to figure out what that a value is. Okay? Well, my a value here is going to be 2. And like I said, referencing the first formula that we have, I'm just going to plug in 2 for a. So if I do that, that would be 2 over s squared plus 2 squared. And I have that down here, okay? So 2 over s squared plus 2 squared would be 4. And that's how we get the Laplace transform of sine of 2t. Let's go ahead and keep practicing a little bit more here. And I'm going to do the Laplace transform now of sine of negative 2t. Okay. Once more, I'm going to put the formula for reference. So we'll be using the sine formula. And just as we did, we're going to be looking for that a value. In this particular problem here, I have the a value emphasized in green. So a was negative 2. And if I go to the formula, I just plug in negative 2 into the numerator. And I also plug it into the denominator, making sure to square it. So if I go back and look at my answer over here in green, negative 2 is in the numerator, negative 2 is in the denominator. If I clean this up here, I'm going to go ahead and pull the negative out front. So I'll finally say the Laplace transform of sine of negative 2t would be negative 2 over s squared plus 4. Again, that's how quick it is. Just find the a value and plug it in. Here's a little bit of an interesting one now. Part C is going to say the Laplace transform of negative sine of 2t. So I'm going to have a negative on the outside. Now, I'm not going to take an a value here of negative 2, and I really don't know what to do with that negative, and I want to take a formal mathematical route here. If I haven't derived a formula for this, the best I can do is just plug it into the Laplace transform definition to see what happens. So let's go step by step here. If I do the Laplace transform of negative sine of 2t, I have the function emphasized in green, and in this next step, I'm going to plug it into the integral, plug it into the definition. What did the definition say? You take the function here being negative sine of 2t, and you integrate it against e to the negative st. Now, assuming the integral converges, I'm gonna pull this negative out here, but we already know, again, I pull the negative out right here, but we already know that the Laplace transform of sine of 2t exists, so I know that integral converges. So all this is gonna come down to is just the negative Laplace transform of sine of 2t, which we already computed. So to sum this one up, the Laplace transform of negative sine of 2t would just be negative the Laplace transform of sine of 2t right there. Okay, so negative 2 over s squared plus 4. Before I go forward to the next example, I want us to compare the answers to part B and C. Notice that I got the same result in both parts. And if we really look at the functions, let's check them out here. Part B, the function was sine of negative 2t. Part C was negative sine of 2t. If we remember properties of sine, sine's an odd function. So I was essentially just taking the Laplace transform of the same function in both parts. And that's why the answers were the same. The last one that I'll finish up with here, just to show a reference, let's do a Laplace transform of a cosine. So let me get the formula up for us so we can reference it. Just as we've been doing, just have to figure out the a value and just have to plug it in, okay? So again, I'm going to emphasize the a value here in green, but doing the Laplace transform of cosine of 2t, the a value would be 2. So I'm just going to plug it into the denominator. Notice the difference between the sine and cosine functions for the Laplace transform. The sine is going to have a constant in the numerator. The cosine will have an s. Okay? The only constant that gets plugged in is in the denominator for cosines. All right? So I have my 2, my a value, plug it in. And then 2 squared would be 4. So the Laplace transform of cosine of 2t would be s over s squared plus 4. The Laplace transform has a nice property of being a linear operator. So now let's look at the linearity of the Laplace transform operator. And let's start by giving the theorem. So I'm going to say let f of t and g of t be two functions whose Laplace transforms exist. Then I'm going to apply the Laplace transform to a linear combination of these two functions. So I'm going to take c1 times f of t for some constant c1 plus c2 times g of t for another constant c2. And what this theorem says is the Laplace transform being linear means you can apply the Laplace transform term by term and then pull out constants. So over here, I do the Laplace transform of f of t, that constant c1 pulls out. And then I do the Laplace transform of g of t, again with that constant c2 pulling out. Let's go ahead and practice this theorem, and we're going to take the Laplace transform of the following functions. The first one here is going to be f of t equals 2 e to the negative t plus 4t minus 2 cosine of 2t. Now, I'm going to go ahead and take the Laplace transform here, and I'm going to actually apply the linearity property of it now. So I'm going to do the Laplace transform term by term. Okay? So I have the Laplace transform of 2e to the negative t plus the Laplace transform of 4t plus the Laplace transform of negative 2 cosine of 2t. Now I have the constants emphasized in green here because by linearity, I can also pull those constants out. Let's go ahead and look at that here in the next step. So I pulled the 2, the 4, and the -2 out of the previous step. So this will be now 2 Laplace transform of e to the -t plus 4 Laplace transform of t minus 2 Laplace transform of cosine of 2t. And now I want to go ahead and focus on taking the Laplace transform of these three functions. In order to do that, I'm going to use a standard Laplace transform table. It's going to be found in most differential equations textbooks, so this is what we're going to use for reference. And I'm going to go ahead, like I said, and take the Laplace transform of the three functions that I have here, the e to the -t, the t, and the cosine of 2t. Let's go ahead and start off with the exponential here. So that exponential is going to have an a value of -1. All right, and I'm going to go ahead and reference the formula over here. So I'm going to plug in -1 for a, and that's going to be done over here in the right column. So I would have 1 over s minus -1, which would give me 1 over s plus 1. And you see that in my first step here, 1 over s plus 1. We now move on to the Laplace transform of t. And I'm going to be referencing this formula right here. Notice that it's t to the first power, so my n value would be 1 here. And when I go over here to the right column, I'm going to plug in a 1 for n. So that'd be 1 factorial over s to the 1 plus 1. I have that emphasized down here in green. So it's plus 4, 1 factorial plus s, 1 plus 1. And then finally, I'm going to do the Laplace transform of cosine of 2t. We've worked with this one already. I just have to know my a value. So a here would be 2. I'll be referencing the cosine formula in the Laplace transform table. So over here in the right column is the Laplace transform. So this will be s over s squared, plugging in the value, plus 2 squared, or 4. So you see I have that here. So it'll be minus 2s over s squared plus 4. And now I'm just going to go ahead and clean up this middle term here in green, the 1 factorial over s, 1 plus 1. And that's going to give me my final answer after taking the Laplace transform term by term. So the final answer here will be 1 over s plus 1 plus 4 over s squared minus 2s over s squared plus 4. Now we're going to look at the Laplace transform of a hyperbolic function, the hyperbolic cosine here. So the Laplace transform of hyperbolic cosine of at. So let's go ahead and do this. Let's take the Laplace transform of hyperbolic cosine of at. And I'm just going to use the alternate definition for hyperbolic cosine. So what do I mean? I'm going to look at the Laplace transform of e to the at plus e to the -at over 2. Again, using the alternate definition. Now I'm going to use linearity, and I'm going to pull out that 1/2. And I'm going to leave the Laplace transform of e to the at plus e to the -at. All right? Once more, I'm going to use linearity, and I'm going to apply the Laplace transform to each exponential separately. So it'll be 1/2 Laplace transform e to the at plus Laplace transform of e to the -at. So how are we going to take the Laplace transform of these two exponential functions? Well, you guessed it. Again, we will reference the Laplace transform table. So notice for the first one, e to the at, okay, that's going to return 1 over s minus a. And when I look at the next one, the Laplace transform of e to the -at, well, I'll have 1 over s minus a. So it'll turn that one to a positive, and that's going to go ahead and give me this result right here. So I have 1/2, 1 over s minus a, that comes from the Laplace transform of e to the at, plus 1 over s plus a, and that's coming from the Laplace transform of e to the -at. We're going to just do a little bit of algebraic manipulation here to clean this up. So I'm just going to combine these fractions with like denominators. I'll have 1/2 s plus s minus a here, and the like denominator will be s minus a times s plus a. Cleans up pretty nicely here to be 1/2. Numerator will be 2s. So go ahead and multiply those out. I'll have s squared minus a squared. You guessed it, that 1/2 and that 2 will cancel. And look, we're going to have s over s squared minus a squared. And if we look over here at the Laplace transform table, look at the Laplace transform of hyperbolic cosine of at. It is s over s squared minus a squared. I hope you enjoyed this lesson on our Laplace transform series. Thank you for watching. I look forward to seeing you in the next lesson.